Recently, I wrote a nuclear and health physics paper titled General Theory of Uranium Particle Radiocarcenogenesis. This paper has been published in Academia EDU, and today we're going to go over this paper. And I'm going to attempt to lay out in layman's terms what this paper is about and what it means to our world. My name is Paul Mobley, and today I'll be representing myself. Those that know me, they know I work with groups and people that I tend to help and work with, but today it's about me, right? So I recently wrote this paper, and on the first page I speak about, how society has learned about radiation. We've learned about alpha, beta, gamma, all that stuff, right? And I go on to talk about how our changing of the allowable thresholds over the years have changed drastically, where in the 1900s, right, the beginning of the century, we were allowed an awful lot of exposure compared to today. The 1950s it came down, 1970s it came down even more, and now today we are at the 5 millirem allowable annual limit for workers, and they are attempting to increase these amounts for workers and the general public. I then go on to talk about this very important equation. And many of you know the name, the equivalent dose, but most people do not know how it's formulated and how this formula and calculation is actually made. I end the first page with talking about the gold standard that they've used ever since Hiroshima and the Japanese lifespan study, and they have utilized a averaging methodology, a linear model, of which we know it is not a linear response. It never has been, and it never will be, right? So we must move away from the linear no threshold model. It is wrong. While we can have a conversation about the threshold part, it is irrefutable that the linear part across the entire dose range is wrong. Okay. So second page. This is where I talk about the kinematics. Where, let me ask you something. When you learned about alpha radiation, did they also tell you about nuclear recoil? Did you know that when this alpha particle comes shooting out, when that alpha emission happens, it's traveling at 3 to 5% the speed of light? That's 9 to 15 million meters per second, right? Now, tell me, can anything at rest shoot something out at that speed without something occurring to that thing at rest? I should hope you say no. This is nuclear recoil. Think of it as like a gun. You're shooting a bullet. The bullet is the alpha particle. The gun would be where that alpha particle originated from. It was uranium, but then it spit out an alpha particle, so everything changed. Therefore, it turns into thorium, right? That's called a daughter. That's a daughter element of uranium. Now, when that alpha particle comes shooting out this way, 15 million meters per second, there's a reciprocal recoil that happens to the daughter. It goes the opposite direction. Equal and opposite force, right? That is the conservation of momentum. Everybody knows this. People seen videos of people shooting guns. We know this, how this works. The problem is they're not telling you about the recoils. They're not sharing with the public about this other thing that happens when this occurs. This goes moving this way. Then the beta happens to thorium. It goes that way, right? So this is the kinematics. These are the formulas that allow us to formulate and calculate the nuclear recoil. All right. Now let's get to the third page. Metallic bonds. You know, say you inhale a very small particle of uranium, a dust particle, and it's around the size of 10 microns, right? And in that 10 micron size piece, you're talking about billions to trillions of uranium atoms. That's a lot of atoms, right? So each one of those atoms in the lattice structure has a bond that keeps them together as one mass, right? And those bonds, they have a breaking energy, the amount of energy it takes to break that bond apart. Now, the typical metallic bond, uranium-uranium bond, it has 0.5 to 1.5 electron volts. The typical uranyl ion, the covalent bond, that has 7 to 8 electron volts to break that bond. Now, the nuclear recoil, its energy is between 70,000 and 150,000 electron volts. We aren't talking about a single bond breaking anymore. We are talking about thousands of bonds breaking. Okay. We move on to the lattice structure. This is a simplified version of the lattice structure of a mass of uranium. These uranium atoms are bonded together. Now, when the alpha emission occurs, there's the daughter. When the alpha emission occurs this way, the daughter is ejected that way. And that's what causes all this displacement. It's no longer the structure. It is displaced. It actually, within picoseconds, it will melt. It will cause this chaos. And then it will quench. And many of them will return back to a lattice structure. The problem is many of them don't, and either return as defects, or in the case of the surface of this PM10 dust particle that you ingested, on the surface, many of these uranium uranyl ions will become detached from that dust particle and no longer be part of the mass, right? So we're talking about thousands of uranyl ions that haven't undergone decay yet, still have to decay their alpha emission, right? And enter around the cells where it's at. Now, relative biological effectiveness. This is what they say. They say that your dose plateaus because the alpha particle's range is 4 microns. That's the radius, or 8 micron diameter, or a volume of 80 micron sphere, right? So they say once the cells are dead around this particle, the alpha particles can no longer cause harm because they don't have the range to get to the other healthy cells. So the dose quickly plateaus and drops off, right? That's what they tell us. The problem is that they're not adding nuclear recoil into the equation. And once those particles are ejected and detached from that central dust particle, there's nothing keeping them to this area. These these displaced Frankel pairs are free-flowing then. They're allowed to enter the bloodstream at that point. So, we see this in research, right? There's actually research on alpha spectroscopy where they have to actually shield the detector from these nuclear recoiled pieces because they keep on messing with their measurements. So they have to put something in between the source and the detector. but which also allows the alpha particles to pass through it. They know about this. This is not some effect that only Paul Mobley knows about. Even the radiopharmaceutical companies know about this. They know about this effect and is an issue. Watch.
An excellent example of that is that, to go back to the howitzer analogy, there's this recoil energy that happens, and it's super cool, and it seems weirdly intuitive for atomic physics. But when an alpha particle emitting radionuclide emits that alpha particle, just like a cannon or a howitzer or whatever, the alpha particle goes flying in one direction, but the nucleus that just emitted it, due to conservation of momentum, it recoils the other way. And so the problem with this, from a chemical and pharmaceutical perspective, is that recoil is strong enough to pop that radioisotope out of whatever was attaching it to the vector or peptide or antibody that was helping it find its way. And so for that reason, getting alpha particle emitting isotopes into cells is very important, because then when they do that recoiling, they are inside the cell and can't redistribute throughout the body. But again, that's just one example of how the kind of fundamental physics and chemistry of these radioactive emissions can have a real world impact on nuclear medicine.